All right, welcome to our lab 8. Welcome back, right? So that's the second video. We're trying to answer the question of what is the average weight of girls with anorexia and how that compares with the weight of girls of similar age in the population at large. So we decided that we meet the assumptions to run a one-sample t-test to investigate this and to use the t-distribution to compute confidence intervals as well. So before we dive into hypothesis testing, it's useful to describe what we found in the best way possible to get an intuition of what's going on. So descriptive statistics is important. And given that the distribution is approximately normal, the mean and standard deviation are useful summary metrics to capture the expected weight of girls with anorexia. We will also add the average weight of girls in the general population of similar age to our descriptors in order to show the comparison, right? How the observed mean weight in our sample compares with that expected weight of the population at large, healthy girls in the population at large. We'll use a bar plot, which you already learned how to do on lab 4, but I'm providing the code here again just to remind yourselves of how that happens. But I would go back to code 4, to lab 4, if you want details of what each piece of the code is doing. I'm not going to repeat that here, but I pretty much copied and pasted the code from that lab here and adapted using the correct name of the data set, what I want on the x-axis, what I want to map on the y-axis. Everything else I pretty much left the same except titles and stuff. So if we do this, we are going to see a bar plot with the average weight of anorexic girls and a standard deviation bar. Now there are a couple of things that are missing here. I would like to add a line that represents the weight of the population at large, to which we want to compare this kind of fixed value that we want to compare this average weight. Before we actually move on, I also noted in our previous labs, and I've been noticing this in R for some time, that R does this weird thing where it puts the bar kind of floating above the x-axis. And there is a way to fix that. So these two things that I'm going to do in this graph are not on lab 4 code, but I will add it here to fix these things. So the first thing, again, everything you're going to add in terms of aesthetics to the graph, you add a plus and you keep layering them on. So the one thing I'm going to do is add a geom horizontal line, age line, kind of with a y-intercept of 130. So I'm putting that kind of in a horizontal line at the level of 130 to represent the average weight of healthy girls in the same age range of our sample. And this is a little trick, so another plus, and this is a little trick to put the bar back to the x-axis. I'm just making it go to 0, 0. I'm controlling that. So if I do this, woohoo, the bar is right there at the x-axis, and we see the line at 130, and we see that the weight of anorexic girls, the estimated average weight of anorexic girls from our sample, is telling us that it's kind of quite below the expected. One thing that's odd about this graph is that the line is right at the top. So we can control up to where our scale goes. And you can play around. You don't need to add this to codes generally. It's kind of not a good idea to do that to begin with before you know what the range of the data is. But you can control that if you want to. So I'm adding that here to make it go all the way to 150 such that this line is not at the top like this. This is not something required at all. But just I think it makes it nicer if it's not right on top of the graph. Otherwise, it kind of looks like a framing instead of looking like what we want it to look like. Of course, if you put a legend on the figure 1 displays the average weight of sample of girls with anorexia and the horizontal line represents the average weight of healthy girls in the population of the same age, that would fix it, right? But I think it makes it nicer when it's not at the top. Now, to get numerical summaries, you can do two things. We've done that to figure out whether the distribution was normal or not. So I'm doing that here again. You can use what you're used to, summarize, and pass as input the data set name. You can ask for sample size because you need that to compute things like standard error. Here I'm passing in X bar, what's the estimated weight of girls with anorexia, standard deviation, and standard error, which is the standard deviation divided by square root of n. So those are kind of nice numerical variables, numerical estimates to put in a table if you prefer, instead of using visuals like this. And if you're asking, what if I want to put standard error in the graph? You can do that by modifying this formula here, just saying that you want to divide that by square root of 17, and that would create, I'm pretty sure this would work, square root of 17, that would create your standard errors instead of the standard deviation. So you can see how that's much smaller because you're dividing by a value. So here it is. If you prefer standard error instead of standard deviation, you can use that in your plot as well. Did you get that? So we're saying we want to plot for the error bar, mean plus standard deviation. You can say, actually, I want the standard deviation divided by square root of 17, the square root of sample size, and you can put that in as well. Another way you can do descriptive statistics that I just discovered is using this function describe from the psych package. The summarize is from the tidyverse package. If you install the psych package, which you have installed in your thing, you can use that as well. The kind of last nice thing about it is that it just outputs everything. Things that you want to see, things that you don't want to see, it's all there. Here you can kind of control what you want on your descriptive table. That's why I like summarize a little better for building tables to represent numeric summaries. But you can do either one of the two when running your descriptive statistics in your independent activity and in your exam. You don't need to do both. You can choose one. Now, in French statistics, we need to set up our hypothesis. The null hypothesis is that the mean weight of anorexic patients is equal to the weight of the general population of the same age, which we know is 130. The alternative hypothesis, which is definitely one-sided because we know a lot about the weight of anorexic girls and we know they have less than, if something, it's going to be less than, never more than. So we want to put our 5% rejection error all at the bottom because the likelihood of it going that way, the other way, is pretty much zero. What we want to know if it's substantially, significantly lower. So it's a directional test for sure. Now we'll do the one sample t-test. And here is the general code that you will need to modify. So this is one, just like I did for the z-test, this is the base code that you need to modify for your purposes. This is it. So t-test is the name of the function, t.test. And input, you get the data frame name and the name of the variable inside the data frame. You tell R whether you want a two-sided hypothesis or if you want a one-sided. You can tell it, I'm doing a less than or a greater than kind of hypothesis. In our case, we're doing a less than. So we just use the parameter less. The null value, you need to put here. What's the average value that captures the null hypothesis? And the confidence level that you wish your confidence interval to be. And again, with one-sided test, you're going to do the 90%. With a two-sided test, you're going to do the 95%. So let's apply this for this particular situation. T.test. Our data set name is anorexia, and the variable we're interested in is weight, which is inside the data frame. We want the less directional test. It needs to be in quotes like this. Our null hypothesis mean is 130, and the confidence level is 0.90. So let's do this. We have the test indicating that the p-value is really, really small. It's 0.1502.2, so it's very, very small. The probability of observing the particular average weight of, where is the average? Of observing an average weight of 83 pounds under the hypothesis that we're sampling from a population that has 130 is very, very unlikely. So we conclude then that the null hypothesis should be rejected because it's not very common to get a sample from a population with that mean weight and get a mean of 83.23. That's what this is telling us. Then the 90% confidence interval comes out kind of weird when we have a unidirectional test. It goes from infinity to a particular value. I'm not so sure what R is doing there. So every time you use the t-test function to run a unidirectional test or a one-tailed test, I just ask you to run it again and just change this to two-sided to get the values of the confidence interval. So you can use the first one you run to get the p-value. That's a p-value related to just one side. But you run it again, just change this parameter to two-sided so you can get the full confidence interval. Of course, I could make you compute that from scratch, but I think it's just simpler to run it again in case of a one-sided test. You're going to run the code twice, one to get the p-value and one to get the interval. As you can see, the value of 130 is not contained here. The highest value of weight that can be expected is actually way below the 130. So there is not only a statistically reliable difference, but the interval is pretty well, it's very precise, and it's telling us that even the most conservative estimate of that difference makes it looks like it's pretty large. It's around like a little less than 50 pounds difference, right? So it's pretty robust and meaningful difference in weight that we can expect from girls with anorexia compared to healthy girls in the population. Decision: reject the null. Now, you guys need to do interpretation as well. That will be a big portion of something of your grade in the exam and also in your assignments from now on. And in doing the interpretation, I want you guys to use the parameters that you obtained from the descriptive analysis from the statistical analysis as well. So, interpretation. The weight of 12 to 17-year-old girls with anorexia is between 81.11 and 85.35 with 90% confidence. The average weight of these girls is significantly lower than the average weight of age-matched girls in the population at large. Note that even the most conservative estimate, which is the higher end here, indicates a very large discrepancy, about 40 pounds. Effective treatments should aim to reduce this disparity. In addition to this, we could say things like the probability of observing a mean weight of 83.2 in a sample drawn from a population whose weight is really low, less than 0.05, right? Meaning that we should reject the hypothesis that the weight of girls with anorexia is just the same as the weight of girls in the general population that are healthy. We'll come back and do problem 2. See you then.